Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to the lecture number 10 for the course of Communication Technology. My name is Engineer Jaffar Ali and I'm your instructor for this course. So, as you all know that in the previous class we have discussed about sampling theorems and the Nyquist criteria that is used for the sampling. I have discussed in detail that what is sampling and how does this phenomenon of sampling occur while you convert your signal from digital analog to digital signal. So we will discuss that in coming classes as well, but this topic was left, so I thought that we should cover this small topic of phase modulation. It's not a small topic, but as you know that we have discussed the frequency modulation and the angle modulation, so I thought that we should cover this topic now. So let's start our discussion of phase modulation. So phase modulation is a form of modulation that represents information as the variations in the instantaneous phase of the carrier wave. Now if you recall, the frequency modulation was basically the variation in the frequency in correspondence to the incoming baseband signal, but in the phase modulation the variation is going to happen in the phase of the carrier wave instead of the amplitude or the frequency. So modification in phase according to the low frequency will be given phase modulation. So this is the kind of modulation, and phase modulation changes the phase of the angle of the complex envelope in direct proportion to the matches signal. The input matches signal will be the one which will have direct impact on the modulation. So suppose that there is a signal that you want to send, and let's call this signal the modulating signal or the message signal, and the carrier signal is this is the carrier signal, and onto which your message signal has to be modulated. So the overall signal will look like something like this equation. I will highlight it for you. This carrier signal C of t, and this AC is the amplitude of the carrier signal, and this is a sinusoidal signal with some phase. So the annotation for this phase modulation is basically given as follow. The same signal, the same equation is basically has the annotation of this thing: carrier amplitude, sine, carrier frequency time, and the phase shift. So this makes the modulated signal something like this. The overall signal will be given as h of phi of t will be equal to AC sine omega ct plus mt plus phi of c. So the greater mt is at a point, the greater the phase shift of the modulated signal is at that point. So it can also be viewed as a change of the frequency of the carrier signal, and the phase modulation can thus be considered as a special case of an FM, in which the carrier frequency is given by the time derivative of the phase modulation. So if you recall, I asked you a question that what is the basic thing that we basically classify this frequency modulation and angle modulation, this phase modulation, into one class of angle modulation. So the answer to that question is given to you over here. So because the carrier signal this PM is basically a special case of FM in which the carrier frequency modulation is given by the time derivative of the phase modulation. So if you go through all of my previous discussions, you will find that I have asked this question several times, and the answer to that question is given here. Now coming towards the theoretical portion and the mathematical portion, the mathematics of the spectral behaviors reveals that there are two regions of a particular interest. For small amplitude signals, PM is similar to the amplitude modulation and exhibits its unfortunate doubling of the baseband bandwidth and poor efficiency. So if you recall the AM, the amplitude modulation, there was two sidebands, and if this this thing corresponds to that AM, this PM basically corresponds to that same AM because of the doubling of the baseband bandwidth. So hence it causes poor efficiency. for a single large sinusoidal, PM is similar to FM, and its bandwidth is approximately given by, you can see that 2h plus 1 into FM, where FM is basically nothing but the you can see that the linear frequency, and it is equal to the angular frequency divided by 2 pi, and h is the modulation index. If you recall, in the PM in the AM it was mu, and now in the PM it is basically h. So this h is basically the modulation index for the phase modulation, and this equation is also known as the Carson's rules for the PM. Carson's rules is a rule, and we will discuss that if you take any interest. We will discuss that in class also, but this is another topic. So let's leave it for now. We will discuss that if it is necessary, if you ask about it in the class. So what is modulation index in terms of this phase modulation? So as with other modulation indices, this quantity indicates by how much the modulated variable varies around its unmodulated level. So this h is basically the variations in the phase of this carrier signal. It is given by h is equal to delta of theta, and where this delta theta is the peak phase. This diagram shows you the schematic of this phase modulation, that how this input beam is then first polarized, and then it is fed into the electropic crystal, and using this voltage signal we will basically get our phase modulated output. You can see that this is our carrier signal, carrier wave, and this is our phase modulated wave. Here E in is basically the input that is given to this setup, and this E out is the output that we gain from this schematic or this system. So it is given as A cos omega t minus kx plus delta t, and if you expand this equation you will get something like. Now let's talk about the multiplexer. So a multiplexer is a device that basically multiplies two or more simultaneous transmission onto a single communication circuit or a single communication channel or a path. So generally speaking, the multiplex circuit must have the same capacity as the sum of all the circuits it combines. So if let's say there are two circuits and you want to multiplex it, so the channel or the link that you want your signal to be multiplexed upon should have the same capacity as a sum as the sum of all these individuals or all those two individual circuits. So this is the first rule of the multiplexing, and the primary benefit of the multiplexing is to save the money, because instead of transmitting two different lines or maintaining two different channels or maintaining two different paths or circuits, you can have a single circuit that you can basically manage. So this is the primary benefit of doing the phenomenon of multiplexing, so that you can save money, and this is not the money which involves capital cost, but it also involves the maintenance cost. So this is the diagrammatic view of the multiplex circuit. You can see that this is the host computer, and this is the front end processor, and this is a 4-level multiplexer. It means that you can actually basically transmit 4 different data onto one single stream of circuit. You can see that instead of transmitting these 4 lines individually, you can have one single line, but this one single line should have the same capacity as the sum of all these 4 individual lines. So in this at the receiving end side, you will have a 4-level multiplexer, and it will basically again demultiplex the single line into 4 different lines. So you can see that this is communication this is system A, let's say this is system B, and this is system C, and the last one is system D. So you can have 4 terminals and one single common shared line. So there are 3 basically major types of multiplexers, but we will discuss only 2 of them. Basically there are 4 mentioned over here. The first one is FDM, that is frequency division multiplexers. The second one is TDM, time division multiplexers. The third one is statistical time division multiplexer. Basically this is a subclass of time division multiplexer, and the last one is wave division multiplexing. So we will discuss all of these one by one. So what is FDM? So FDM is basically a technique in which you divide your circuit in such a way that it basically separates the frequencies. The circuit is divided into series of channels, each transmitting on a different frequency. It is mentioned over here that the circuit is divided into a series of separate channels, each transmitting on a different frequency. And if you want to make sure that there is no interference in between these frequencies, you can also keep a guard band between them, so that you can keep one channel from leaking over into another channel. So this is the thing that you can use for the reduction of the interference. And frequency division multiplexers are somewhat inflexible, because once you determine how many channels you require, it may be difficult to add more channels without purchasing an entirely new multiplexers. So this point basically illustrates that, let's say you have bought a multiplexer, and in the future you want to add more channels, but the multiplexer that you have already bought has not more room in it, so you will have to replace that multiplexer. So that basically increases the cost. So this is the major drawback of this FDM, and in spite of this small disadvantage, FDM is very vastly used nowadays. This is you can see that the example given to you. Let's say this is the total 3000 hertz of available bandwidth, and you divide it. You can see that from 2200 to, let's say, 2600, and then you basically it starts from the bottom side. The first you have to let's say leave some guard band to reduce the interference, and then you start your frequency from 400 to 800, and then again you leave the guard band of 200 and start from, yeah, you can see that you have left the guard band of 200 hertz, and then you have started from 1000 and you have gone towards 1400, and again you have left this 200, and then you have started from 1600 and you have gone towards 2000, and then again you have left 200, and you started from 2200 and you have gone towards 2600. So this is a kind of setup, and you can see that the total bandwidth basically available used over here is 2800. You can see that because this is a guard band of again 200, so 2600 plus 200 makes it 2800. So the total available bandwidth will be basically 2800 for this case. And this is the multiplexer side, and this is the demultiplexer side. These two processes are basically reciprocal of each other. The first FDM is basically the one that basically converts these 4 signals or merges this 4 signal onto one line, and this the other thing is this demultiplexer is basically the one which basically deseparates this one line into its corresponding users onto a different channels. I will share the link of this topic in the previous semester I have taught you. I think this topic has been already gone through our discussion, so I will share the link of that lecture as well. Moving swiftly on TDM, this is time division multiplexing. So in time division multiplexing, instead of sharing or doing the things horizontally, we do it vertically, and we basically divide the time and we allocate time on the circuit when the data are not transmitted, so the same capacity used or by the other user, and the resources are not being wasted. So this is a more efficient way of doing the division of the resources. But the only drawback of this is basically all the users will have the same priority in despite of their payment procedures or their priorities. So to avoid that, and to you can see that all the users will have the same priority. The first packet will be taken from A. Let's say this is your A, this is your B, the third line is your C, and the fourth line is your D. So you can see that the first packet will be taken from A, the second is taken from B, the third is taken from C, and the last one is taken from D. And the list goes, this thing goes on. But what if this A has paid twice as compared to the B, C, and D? So this is not the thing over here. So to tackle that scenario, we are going towards this statistical TDM. And in a statistical TDM, there is a circuit which basically shows that how much priority, if A has twice of the priority as compared to the B, C, D, so A will be given 2 slots as compared to the B, C, D. So in statistical TDM, the circuit will be something like this. This will be double A. 2 time slots will be given to the A, and B, C, D will be given 1 time slots each. So this is a statistical TDM, and I will also share the link of that previous video that of the data and computer communication, in which I have taught you this topic. I hope this is understandable to you, and if you have any questions, you can write it down and bring it into the class. I hope that you have learned quite a lot from this lecture. I hope to see you in the class. Thank you very much. Allah Hafiz.